Hello. So at the end of the previous video, I gave you this exercise, and these six numbers. From these six numbers, try to find the covariance, which will be pretty much the same as this structure, like follow the same algebra like this. So let's do that. Six numbers, and I gave you the averages, so you can calculate the deviations without much difficulties. So deviations are calculated this way: deviations for the temperature in Fahrenheit and deviations for the GDP per capita in $1,000, and then multiply them for each country. You get these three numbers, and then take their average, but the denominator is n minus 1. So the covariance is sum of these three numbers divided by 3 minus 1, which is minus 270. Earlier, what was that? The covariance, I forgot to call this number. The covariance in the earlier example was minus 150,000, and now it is minus 270. In both cases, the direction of their relationship is negative. Okay, I hope you did the work. And now let's think about a little more carefully. What we did, just the difference between this and this is just changing the units. They are the same temperatures. Just one is represented in Celsius and the other in Fahrenheit. And GDP per capita is even the same, because one has 3 zeros and the other does not have 3 zeros. So basically, those two examples have the same data. Underlying data are just the same. There is no reason to be different. So, however, the covariance is different. So, the covariance is different, which is a problem. We are working on the same variables with different units, but it looks like the relationship's different, which is not desirable. Therefore, we are going to study what's going on, what happens in the unit change. Here is the answer. So in our example, the Fahrenheit temperature in Fahrenheit has this linear transformation of x. So Fahrenheit is 1.8 times Celsius plus 32. And Z, this is so GDP per capita without 3 zeros, after deleting 3 zeros. So just divide by 1,000 from the original GDP per capita. Then, and because of these two linear transformations, the covariance changes this much. It can be explained by this rule. The covariance for the new random variables is affected by those two multiplicated numbers. So you multiply 1.8 to x and then 1 over 1,000 to y. So these two guys determine the relationship between the covariances of the original and the transformed random variables. And remember, exactly this is the another thing you have to watch here is plus 32 does not affect at all. So additive numbers, like when you add or subtract something, it has no effect on the covariance, because we are looking at the slope, like parallel shift going up or down or left or right makes no change in the slope. To have a slope change, like it's either like going down or vertical, so only affected by multiplications, but not additions or subtractions, right? So it's pretty familiar. It's very similar to the rule we learned in chapter 4. variance had a very similar rule like this, a formula like this. In general, this is a general rule. Suppose that you have original random variable x and y, and then you make new random variables, from the original x and y by some linear transformations, a, b, c, d, multiply a and c, and then add b and d. And then the new covariance is the original covariance times 2 multiplications. B and D has no effect. So this is the underlying relationship between the two examples. I intentionally gave you two examples, and then I think it explains it's more clear what we were doing. By the way, as I said, I understand how the covariance changes, but anyhow, still it is not desirable. Temperature in Celsius, temperature in Fahrenheit, basically does not change anything. Still, the relationship should be the same, but covariance is not the same. So we are going to modify the measure. And also, you have to keep that in mind. The magnitude of a covariance doesn't mean anything. So, like for example, 150,000 or 270 are basically the same relationship. So the scale does not make any difference. So the magnitude, the size, the absolute value means nothing. In covariance, only the direction matters. By the way, means nothing, I mean you cannot interpret where this number has come from. Those two numbers has no direct interpretation, but later the covariance is important in calculating something else. So those magnitudes will be used later, but they do not have any direct interpretation. So that's what I wanted to say. Don't make me wrong. So anyhow, this is a problem. The magnitude is not interpretable. So we are going to modify the covariance to capture the strength of the relationship from the magnitude, from the absolute value. So like ideally, we want to say that like minus 150,000 should be a much stronger relationship than this one. But they are not in this case. They are the same relationship. So we don't like that. So we are going to make another measure that has the property, that is the correlation coefficient. Now, how do we make a correlation coefficient? The idea is we standardize. We use the same standardization we learned in the normal distribution chapter. Again, if you divide the deviations by standard deviation, then now it's unit free. It's unit free. So the correlation coefficient is defined as, so remember, we used x deviation, y deviation here for the covariance when we calculated the covariance. But now we use standardized deviation, not just deviation. Use standardized deviation and do the same thing. Take the average with denominator n-1. And then in the end, simple algebra shows that it can be understood as covariance standardized by both variables' standard deviations. So because covariance involves two variables, when you standardize it, you have to use two standard deviations. Like this. When covariance is multiplied, it's multiplied by two numbers from each variable. So like that, standard deviation should be used for both variables. So two standard deviations in the denominator, and then you will get the correlation coefficient, which is usually denoted in this way. CORR x comma y, correlation coefficient between x and y. Then it's really nice. This correlation coefficient is really nice because it always lies between -1 and 1. So the scale is fixed, right? It does not get a number like this, crazy number like this, right? It's always interpretable because it always lies between -1 and 1. So it is standardized and it shows the strength. If the correlation coefficient is close to 1 or -1, that means that relationship is really strong. So close to 1 or -1 means a strong relationship. But if it's close to 0, then the relationship is weak. So it captures not only the sign, the direction, but also captures the strength by the absolute value. The absolute value shows the strength, which is much better than the covariance. So like this, for example, if you compare these two graphs, you can simply summarize their difference using the correlation coefficient. The left one has correlation coefficient of 0.5 and the right one has 0.9. So much stronger relationship, which means the errors are smaller, deviations are smaller, and all the observations are closer to the trend line. The trend is much clearer, right? And this is an example of a perfect linear relationship, either 1 or -1. So when the correlation coefficient is 1, that means all the observations are aligned in a perfect straight line. Of course, it does not exist in reality. In practice, you will never see something like that. But in theory, in principle, you can imagine something like this. And if it's -1, also perfect straight line, but downward sloping. So strength is both of these two graphs have perfect strong strength, but the direction changes. And one is going up and the other is going down. Okay, and more examples. These are some cases where the correlation coefficient equals 0. First example is when observations lie flat. Like so, when x increases, there is no clear trend in y. Y does not increase nor decrease. Or this is another extreme case. It's vertical. The trend line is vertical. Or this is a case where just nothing. There is no pattern. It's just like round, but there is no like it's hard to make a line going through the dots. And the last example is when you have nonlinear relationship like this. Like suppose that the data look like this, which has a very strong relationship. As you can see, though the relationship is quadratic. It is a perfect quadratic relationship, but our framework cannot handle quadratic relationship. Our framework only is limited to linear relationship. So the best you can do is making a straight line, drawing a straight line that best describe the quadratic function, which means it's just a flat line like this. And of course it does not fit well, but anyhow it's flat, so the correlation is 0 seemingly. So if you calculate, correlation will be 0, but you have to be careful. It doesn't mean there is no relationship. There is no linear relationship, but there is a very strong quadratic relationship. So as a word of caution, you have to be careful in interpreting this kind of data. Okay, then in the next let me show you. So like from the data from the first example, we know the covariance is -150,000, And then using 3 variables for temperature, you can calculate the standard deviation, which is 15. And using the 3 observations from for the GDP per capita, the standard deviation is 13,000, about 13,000. Then, so you need covariance and 2 standard deviations, then simply standardize. You will get the correlation coefficient, which is minus 0.7559. It's a negative relationship, and the absolute value 0.75 means quite a strong relationship. Okay, then I want you to try this again. For the second example, can you show me how to calculate the correlation coefficient for this new pair of random variables? We'll and do this exercise and come to the next video. Then I will continue there. See you there. Bye.